So we're winding up our lessons on stoichiometry. What we're doing today is practicing. So here's the homework problem that was assigned. If 2.35 grams of aqueous hydrochloric acid is reacted with 2.11 grams of potassium carbonate at STP, that means standard temperature and pressure, and 10.0 centiliters, which is the same as 0.100 liters, of carbon dioxide is collected, what is the percent yield? So we're starting with aqueous hydrochloric acid and potassium carbonate. Potassium is K, carbonate CO3, potassium has a 1 plus charge, carbonate has a 2 negative charge, so we need 2 potassiums to charge balance the formula. And so this is aqueous, or did we? Well, it doesn't say it, but it is aqueous because it does dissolve in water. Carbonates are mostly insoluble in the solubility rules. However, there's an exception for group 1 metals bonded with carbonate. So then this compound, because it has a group 1 metal on the front, would be aqueous. It's also, one of the other solubility rules says that any salt with a group 1 metal is going to be aqueous. So in both rules, this is aqueous. And so what we're going to do is look at what kind of products we can make here. So we have an acid here and a salt, or an acid and an ionic compound. And the most likely thing that can happen here is that the front part of this goes with the back part of this. It's called a double replacement reaction. The front part of this goes with the back part of this. So let's put this H over here with the CO3. And this is where bells and whistles should be going off in your head, because we know this is going to decompose. And I'm going to do this in 2 steps. You didn't have to do it in 2 steps, but I'm going to do it in 2 steps. Carbonates with a hydrogen on the front are going to be aqueous. It will be. I haven't gotten there yet. What I'm trying to do is to write down the products over here first and then balance it, because most of the time when you write your products first and then figure out the physical states, that's how you know if you have a driving force. Okay? So then potassium is going to go with chlorine, and remember group 1 metal salts are aqueous, so this is aqueous. So this doesn't actually stay like this. The reason this, as we look at this, if we had 2 aqueous substances over here, we would not have a driving force. You have to form either a solid, water, or a gas. So right now it looks like we're not going to have a driving force, but like I said, bells and whistles should be going off when you put hydrogen with carbonate, and you should know that's really carbonic acid, and it immediately breaks down. So really, instead of these products, this is going to break down into H2O, which is a liquid, there's your driving force, and CO2, which is a gas, and there's another driving force, and KCl. Okay? Now, we have to balance the equation. We're doing stoichiometry here. We're going from one chemical species to another. We're going from one of these 2 reactants to a product. First of all, we've got to find out what our limiting reactant is. So we're going to have to balance the equation. To do all that, let's do an atom inventory. HCl. I didn't mention this, but that's potassium has a +1 charge. Chlorine has a 1 negative charge. So that's balanced as written. We've got potassium here, and carbon and oxygen. Find my other marker. So initially we have 1 hydrogen, 1 chlorine, 2 potassiums, 1 carbon, and 3 oxygens. And on the other side of the equation, I have 2 hydrogens. I have 1 chlorine. I have 1 potassium. I've got 1 carbon, and 1, 2, 3 oxygens. Remember, we're going to save oxygen for last and hydrogen next to last. So we're going to start with the potassium here. And in order to balance this, we can only put coefficients in front of the species, the chemical species. We can't change the formula. We can't put any numbers in the formula. So we need to put a 2 in front of the species that contains the potassium, and that's going to change the number of potassiums and chlorines. And that's going to give us 2 potassiums and 2 chlorines. All right, again, we're saving oxygen for last, hydrogen next to last. The next thing to balance is the chlorine. Since I have 2 on this side, and this is the species on the left that has chlorine, I need to put a coefficient 2 in front of that species, which is going to change the number of hydrogens and chlorines, and that's going to give us 2 hydrogens and 2 chlorines, and everything's balanced. So we're ready to start our stoichiometry now. First, we've got to find our limiting reactant. So we're going to calculate from one of the 2 reactants to the other. We're given a mass of 2.3 grams of hydrochloric acid and 2.11 grams of potassium carbonate. So it doesn't matter which one of those 2 you start with. I'm just going to start with the first one listed, 2.35. Regardless of which one of these 2 you start with, you're going to get the same, not the same answer numerically, but you're going to be able to reach the same conclusion about what your limiting reactant is. So we need a molar mass of hydrochloric acid in order to convert to moles. So hydrogen is 1.008. Chlorine is 35. I think on here it's listed 45. Okay, 35.45 on your periodic table. Okay. Since we only have one of each of those in the formula, remember we don't consider the coefficients here when we're calculating molar mass. It's 1 hydrogen and 1 chlorine because that's what we have in the formula. So we don't have to do times 1 over here because we really only have 1, so we can just add this up then. So that comes out to be 36.458. We do need to round off this last digit because there's an empty slot right there. This is grams of hydrogen chloride or hydrochloric acid. Round that off to 36.46 grams of hydrochloric acid, and that's equal to 1 mole of hydrochloric acid. Now, this is actually, just this part right here is actually the molar mass. But in order to set this up in an equality statement to build conversion units, I ask you always in this class to write it out as an equality statement. So in my class anyway, you lose points if you don't do that, okay? So we're going to put the mass of hydrochloric acid on the bottom, 36.46 grams of HCl, and we're going to put the moles of hydrochloric acid on the top. And we did that because it allows us to cancel out grams and hydrochloric acid, and that leaves us with moles of hydrochloric acid, which is where we have to be. In order to go from one species to another, we've got to go from moles of one thing to moles of another. So we now have it in moles, and we're ready to do the molar conversion. And for a molar conversion, we did a molar ratio. And what we're going to do is to take the number of moles in the equation up here, and this does mean 2 of this formula unit, but if everything in the whole equation is multiplied by Avogadro's number, we have 2 moles, 1 mole, 1 mole, 1 mole, and 2 moles. So we can use that ratio, 2 moles of hydrochloric acid, and what we're trying to find right now is how much of the potassium carbonate is needed to completely react with this amount of hydrochloric acid. So we're going to go to 1 mole of potassium carbonate, cancel out units and species, and we have to calculate a molar mass to get that back into mass. You can't just go directly from mass of one thing to mass of another. You've got to go through moleville to get there. So we've got potassium and carbon and oxygen. Potassium on your periodic table. In this class, this is a preparatory class for AP Chemistry, so we use the periodic table that's used for the AP test. And on this periodic table, the atomic mass is 39.10. And the atomic mass for carbon is 12.01. And the atomic mass for oxygen is 16. Now this is atomic mass, and it's listed in units of atomic mass units, which are symbolized with a lowercase u. But instead of calculating molar mass, we're actually converting that into grams to get the molar mass. It's just simpler to remember it that way. So that's why our answer comes out in grams down here. All right, so we have 2 potassium, so we need 2 of these atomic masses for potassium, and 1 of these for carbon because I only have 1 carbon, and 3 of these for oxygen because I have 3 oxygens. Okay, so 39.10 0.10 times 2. Oops, the wrong button. Clear that out. 39.1 times 2, 78.20, 12.01, and this is going to be 16 times 3, 48. That's sad. I should be able to do that in my head. I don't know why I'm having issues with my allergies today. At least that's my excuse. I'm going to stick to it. 18, carry a 1. No, it's about to be 13. Is that right? Nope. Did I do it wrong? 72. Oh, I hit a wrong button. Gracious. Okay, 78.2 plus 12.01 plus 48. Okay, 138.21, good. And this is grams of potassium carbonate, and that's equal to 1 mole of potassium carbonate. Now, over here I had to round off because I had an empty slot under this 8. Anytime you're adding or subtracting numbers such that you have an empty slot to the right, the resulting digits must be rounded off. Here I didn't have any empty slots, so there's no reason to round off. So let's see, we want to put moles on the bottom this time because I want to cancel the moles that are on the top here. And we're going to put 138.21 on the top. Cancel out moles, cancel out K2CO3, and do the math. Or some students want to say, do the math. .45. That's grams of potassium carbonate, and I want to round that off to the least digits of the measured and calculated numbers. This is a measured number, calculated number to calculated number. Those are the ones that matter. This has the least digits, 3 digits, so I want 3 digits here. So that's 4.45 grams. So this is the amount of potassium carbonate needed to completely react with this 2.35 grams of hydrochloric acid. In the problem, I only have 2.11 grams of potassium carbonate, and therefore I don't have enough to completely react with the hydrochloric acid. If I don't have enough of it, that's the limiting reactant. Does that make sense? Okay. So therefore, K2CO3 is the limiting reactant. Okay, so now we're going to calculate our way to the product we're looking for, starting with the amount of K2CO3 in the problem, what we're actually given, which is 2.11 grams. So 2.11 grams K2CO3 over 1. Got to convert it to moles. We already have a molar ratio here. Cancel out grams and K2CO3. We're going to use a molar ratio to go from moles of this to moles of the product we're looking for, and in the question it's clear we're looking for carbon dioxide. And the equation, there's a 1-to-1 ratio between potassium carbonate and carbon dioxide. Okay, 1 mole of this and 1 mole of this. So we're going to put 1 mole of K2CO3 on the bottom, because that's going to cancel those moles in that species, and then 1 mole of CO2. Cancel out the units of moles and the species K2CO3. Now, I can see when I look at the problem here that my product is in liters. So in order to do a percent yield, I also want my theoretical yield for that product in liters. Okay? And so instead of using a molar mass for this, I can use molar volume, and molar volume is really simple. You just have to remember that 22.4 liters of any gas, in this case CO2 is a gas, we said so right up here, okay, of CO2 is equal to 1 mole of CO2. I want you to always write down those equality statements to justify writing this conversion unit so you don't get confused, okay? Writing it down helps you not to be confused, okay? I'm sure it helps the environment not to use up so much pencil, what we call lead, it's graphite, or paper, but, I mean, it's more important that you get a good grade, okay? So help yourself out and write it down. Writing it down and keeping a record of it helps you to find it and focus on it and remember what you're doing because there's a lot of stuff to keep up with here. All right, so we want 22.4 liters of CO2 and 1 mole of CO2 on the bottom. Now, it's really important to be careful that this only works, this ratio, this equality, only works as long as the gas is at STP, which is standard temperature and pressure, and the problem says everything is at STP. So we can use this ratio so long as we are at STP. Okay? Standard temperature and pressure, we won't really need to know this until the next unit, but standard temperature and pressure, let me back it up. We won't need to know this to be able to use it much until the next unit, but you need to know standard temperature is 0 degrees C, and standard pressure is 1 atmosphere. All right, so we can cancel moles, we can cancel CO2, and we're ready to do this math. So 2.11 times 22.4, enter, divided by 138.21, whoop, back up, 121, and I get 0.34, 0.341972369. Now your calculator may have some fewer digits on the right. You just write down what your calculator actually has. This is liters of CO2. Underline all but the significant digits. Got 3 significant digits here, 5 here, 3 here. So we want 3 significant digits in our answer. 0.342 liters of CO2. And so that's our theoretical yield. Okay? The percent yield then is calculated by putting this actual yield over the actual yield, which is supposed to be 0.100 liters. .342 liters of CO2, and then multiply that answer by 100. Again, we're going to look at the number of significant digits here and make our final answer match that. That is liters of CO2. Okay. All right. If you didn't do as well as you would like on that last problem, here's a makeup problem. If 15.00 grams of aqueous nitric acid is reacted with 25.00 grams of rubidium carbonate and 0.55 liters of carbon dioxide is collected at STP, what is the percent yield? So here is one more practice problem. If 2.50 grams of iron is placed in an aqueous solution containing 25.00 grams of antimony 3 chlorate and 3.00 grams of antimony metal is collected, what is the percent yield?